I I wanted to use this video to explain how the DDSCAT input file should be prepared. I have done a video many years ago that explained like how we run DDSCAT calculation, but I didn't explain how we actually prepare the input file. So I assume you have installed DDSCAT 7.3. And inside DDSCAT 7.3, there will be some examples of input file. You can copy one of them and tailor them. So this is an example of the input file that we use very often. And I'll explain some of the input, like what you need to change, what you don't need to change. So here's just a copy of the input file, which the file name, we name it DDSCAT.pal. You can find DDSCAT.pal within the DDSCAT 7.3. Okay, so here's the file DDSCAT.pal. The first few lines here, these options, we never usually don't change. We rarely change any of them. So it is related to the DDSCAT, the whole kernel, how it's solving the equation. This is like this one, NOTOQ. We don't usually change anything. We just go with that one. We never played how does that matters, okay? And then PBCGS2, again, that doesn't matter too much. We usually don't change. And as you can tell, this is related to something to the fast Fourier transform, doesn't really matter. Now this one, FLTRCD, this is related to how we assign the alpha polarizability based on the dielectric constant. This one we played a little bit, but we usually always use FLTRCD. I think this is the latest version of DDSCAT. The Professor Drain has developed this method. So we could pretty much stick with that. Okay, and then this one, we don't change. All right, so this one, initial memory allocation, we need to change this one. You can try to increase that number as large as possible. When we set 300 times 300 times 300, that's already pretty much like almost reaching the limit of the computer that we can run. And then the target geometry, this is the part that we actually do change quite a bit. So in this particular example, we use this input style called spheres_n. You can look up DDSCAT manual that explain different types of input method, like how to generate target. Sphere n is the type that it will allow you to specify how many number of spheres that you have, and then you need to specify the coordinate of spheres. So this is a very useful module to study nanoparticle assembly. So the one that we particularly use this one here is looking at silver and gold dimer coupling. And so we use the sphere n, okay? And then if you're using sphere n, then you need to follow by the next line, which is specify 75. This first one is the dimension of the target geometry that you were mapping. So in our cases, I will show you what sphere.data later on. But so that's one dimension. And then spheres.data is the file that contains the coordinates of the particle where they are in the radius. So I have the next one I explain, show you how the sphere.data look like. Okay, so number of composition. In these cases, I said 1. You can say 2. And if it's silver and gold heterodimer, then you definitely should say 2. And then if you say 2, then you should follow by 2 files that indicates what's the refractive index file that you need to prepare. So because this one I said 1, there's only looking at the gold dielectric. I think this one we looking at maybe like 2 gold nanoparticle coupling together. So it is only one dielectric file called gold diel.tab. So this is the refractive index for 1, okay? And then the other parameter, this one, NRFLD, you should set to 1 to calculate the near field. If you don't calculate the near field, you just set set to 0. So we spend a lot of resources to get the near field on the particle surfaces carefully. So we always set 1. And if you set 1, then of course you need to set like how much, because you need to calculate the near field, you need to have the lattice simulation that cover the sphere and extend it beyond the sphere. So this is what it is about. This is 0.1, 0.1, 0.1 is the fraction of extension of the volume in the x direction, y direction, z direction, okay? Now these number, we don't much change. You don't need to worry too much. Maximum allowed, mixed inter, that usually doesn't matter to us. Yeah, neither these ones, so usually don't worry. The 0.5 ET, ASC, and number of angle. This is also, we don't worry too much. It is something related to when you calculate the angle of scattering, so we don't worry too much. Now you need to worry about the wavelengths, which wavelengths you wanted to simulate. So we normally set up the simulation. We actually do, what we do is actually different lambda value, we make a directory. And then this lambda value, we right now in this input file is 2 text file. And we will read this file and then replace these 2 lambda file with the actual number of wavelengths that we will run. So for example, if it's a 450, we have a script file that will replace the lambda with 450 nanometers. Okay, so that's what we do. And then as you can tell, this one is the surrounding dielectric constant. We normally prefer to run it at 1.33 to represent aqueous water. Okay, so you need to worry about effective radius, the particle effective radius. Now, if you're running just one particle, say suppose you're running a single particle with say 50 nanometer gold, for example, then of course this A effective is just 0.05 micrometer, right? Okay, the tricky thing is if you're running like a 2 gold nanoparticle, each is 50 nanometer, then the A effective that you should enter over here is related to this 50 nanometers through this equation, this relationship. The idea, let me explain to you. The total volume, 3/4 pi A effective cube, should equal 2 times 3/4 pi, the radius A for the particle radius, right? So therefore, A effective is 2 to 1/3 related to the particle radius A. So you want to make sure that you enter this A effective correctly for your system, depending how you want to model it, okay? And then, right, okay, then the next thing you worry is about the polarization, the light, what kind of polarization you do. So yeah, this is an old input file. We normally always set the next parameter to 2. So we'll do 2 polarization. You can specify the first one along the, polarization state E01. In DDSCAT, the K is always propagating in the X direction. This is X and Y. So the vector K is always this direction. But the Y, the electric field could be the Y or could be the Z, okay? So once you specify the first one, if you set I ortho equal 1, so it will actually generating 2 polarization. They will run the simulation with electric field in the Y direction, but it will also run the simulation with the electric field polarized in the Z direction. So you have to look at the output carefully. It will generate 2 E field, E1 and E2. Associated with the 2 polarization. The rest, yeah, this is parameter doesn't really matter. It's just a matter of how many writing out. Okay, the target orientation took me a while to figure out. The example over here is actually there's only one orientation, but you probably should read the manual, talk about like if you wanted to rotate the target, how you want to rotate them. So if you want to ever rotating, that's where you rotating the targets using these 3 angles, okay? And then I specify R wavelengths, I radius, RO. These we always set to 0. Yeah, we don't change. Select elements of Sij. This is related to calculate the scattering. So I'm gonna skip that for a moment. These are not usually changed. Yeah, and then you always specify laboratory frame that's where you calculate the scattering. So if you're not very sure, if you just like want to calculate extinction coefficient, absorption, you really don't worry too much about these scattering. Scattering is a whole another issue. Okay, so that's about what DDSCAT.pol, that file look like. So here, the next slides, I give you the example, the spheres.data that it is called by the DDSCAT.pol. So here's the file for the spheres.data. You begin the first line, you tell them it's a 2. There are 2 spheres. And then next 4 line, actually DDSCAT is written in Fortran code. So when you process the input file, you have to specify how many lines. So these 4 lines actually was ignored in the code. Up to here, it's all ignored here. So you can put whatever the comments you want, okay? And it reads, really read here. So this will be the first particle, because I specified 2. This will be the first particle XYZ direction, and then this particle, the radius A. And then it will also specify what kind of composition it is. So my sphere.data example over here, actually I'm using silver and gold, like a dimer situation. So I have 0, 0, 0. The first one is at 0, 0, 0. The second one is 0, 22, 0, right? So this is 0, 0, 0, and the radius is 10. Another one is at 22, also radius 10. So you can see the gap is actually 2 nanometer gap, and that's what it is. But then of course the dielectric file should be 2. So the DDSCAT.pol, you should specify that you have 2 dielectric files. One is silver, one is gold. Okay, the last thing I need to show you is how our script file to run on HPC run the DDSCAT look like. So this is our script. We use our HPC use SBatch to submit jobs. So this is an actual submission job. So we define the CPU, the nodes, the memory, job name, all of that. And we define an array, 300 to 800 at every 5 nanometers. So we actually run the simulation from 300 nanometer to 800 nanometer at every 5 nanometer interval, okay? And so you can see like what we do to run this, you just like submit, right? So actually we submit a slur of jobs one by one, okay? And then we set lambda value is based on these values, based on the slum array task ID, was it 300 or 305, etc. And then we get the lambda value, we make a directory that begins with like a lambda 300 or 305. So we have simulations around in each directory. And then we make that directory and then we copy, we originally prepared a directory, the file, which inside in this directory files, we have DDSCAT.pol, right? And then we also have the silver dielectric file. And we also have gold dielectric file, okay? And then we also have spheres.data. Yeah, these are the file that was put in the files. And then we just like copy all of these files into this directory that we will run the job. And then we change the DDSCAT.pol inside this lambda, the string, by the actual value of lambda. And then we just set the DDSCAT executable where it was, and DD post-processing executable where it was. And then you just run the DDSCAT. When you finish, you can run DD post-process if you want to. Yeah, so that's it. That's really explain everything and how we do it to run the DDSCAT. And of course, after you finish, you run all of the directory. If you want to know the extension as a function wavelengths, we have another script file that goes to each directory, pull out the extension, the absorption, the scattering, the near field data, etc. All right. So hope this is helpful to you.